Okay, so good evening, everyone. Welcome to your third discussion session in Mechanical Behavior of Materials. I am Pragyandipta Mishra, the research scholar from Department of Applied Mechanics and Biomedical Engineering at IIT Madras. Today, we'll be discussing about viscoelasticity and tensile testing and solving problems on the same topic. So let's begin with our first topic of today, viscoelasticity. So, what exactly is viscoelasticity? Now, till now we have been studying in container mechanics about elasticity and plasticity, right? So in elasticity, what did we observe? We observed that materials have a property of getting back to their original shape and dimensions once the load is removed, right? That is what elasticity was supposed to be. While in plasticity or plastic deformation, what we have noticed is that the material did not regain completely, right? There was some level of permanent set or permanent deformation which has already been present in the material. Viscoelasticity differs from both of this. So in viscoelasticity, what happens is some particular special materials, they will show time-dependent deformation behavior. So what will happen is essentially when we load the material initially shows some deformation, and then once we remove the load, it does not immediately regain its original shape and size. It takes some time. So this time-dependent recovery is what we know as viscoelasticity. Now, understand that in viscoelasticity, the material will still regain its original shape and size. So it is similar to elasticity in that way, but it takes some time for it to recover the original shape and size. So therefore, it is not exactly similar to elasticity, but has a difference called viscoelasticity. That's why we call it viscoelasticity. So let's write down the definition. I hope you're able to. Which is recoverable. Okay. So what is happening is when you apply a load, there is an instantaneous elastic deformation, and it keeps on increasing and does not stop with time. Okay. So one important point that you can note, which is the difference between viscoelasticity and elasticity, is that when the load is applied, there is an instantaneous elastic deformation. So this is similar to elasticity in this way, right? There's an instantaneous elastic deformation as soon as the load is applied. This is similar to elastic deformation. However, the deformation will keep on increasing and it does not stop with time. So it is a time dependent deformation behavior. Okay. Now you would say, okay, like this is similar to elastic behavior, but showing a time dependent behavior, right? And it's kind of elasticity with a time dependence elasticity. You can think of it this way. Then similarly, if you might ask me, what is a time dependent plastic deformation behavior? What do we call that? So there is another phenomena for that. It is known as creep. So if I have to define creep, it is time dependent plastic deformation. While viscoelasticity is time dependent elastic deformation. Okay. So this is a major difference between viscoelasticity and creep. Creep is plastic deformation, while viscoelasticity is elastic deformation, even though both of them are time dependent. Okay. Now, this viscoelastic strains that you see is something that is not necessary when we are dealing with structural materials. So, if we need to uh, use these materials for structural applications, these viscoelastic strains are completely undesirable. Therefore, in order to choose structural materials, we have to choose materials which show very small viscoelastic strain. So, therefore, metals are the best examples of materials which do not show much viscoelastic strain. However, if you look at polymers, different kinds of polymers, they have this viscoelastic strain or viscoelasticity. They show viscoelasticity as a behavior almost all the time. Therefore, these materials are definitely not used for structural applications, but they are used for other applications where viscoelasticity is desirable. So, therefore, this is something that you can remember, that for structural applications, viscoelasticity is undesirable. Okay. So now let's look at what is the mathematical description of viscoelasticity. There are two components to viscoelasticity, right? Like we discussed. There is time dependent deformation, right? So there are two components to it. So therefore, we have to break it down into two components which can represent its both the behaviors, right? Or we have to represent it using one component which can represent both the behaviors. So it is not possible for us to define a component that can represent both the behaviors simultaneously. So therefore, we'll break it down into two different components. So first component is spring. Okay. So in spring, if I just draw regular spring, let me just and some force, let's say Fe is active. This is some spring constant Ke. So your strain or deformation, let's say, the spring will be Fe by Ke. It's not deformation, it's strain actually. So your strain is equal to force, your force applied divided by the spring constant. So this is your spring constant. Okay. So this is how you can get the relation between force and strain. Now in dashpot, so there's another component. So this spring is representing your sudden instantaneous application of load and it just moves directly, right? Now you want to represent the time dependent behavior. So there's another component that you can use to represent that, which is known as dashpot. So this shows, like, this is similar to a behavior where you have a piston in a cylinder kind of arrangement, and you're applying some force Fv. Okay, so let the constant be Kv. Okay, just a second. Let's check if recording is fine. I hope the recording is going fine. Yeah, it's fine. The recording is fine. Sorry about that. I'm just checking if the recording is okay. Yeah. So for dashpot, the how strain is related to the force is given by EV is equal to EV dot is equal to FV divided by KV. Now what is EV dot? It is the instantaneous strain, okay, or change in strain at a small instant of time. So I can write EV dot as dEV by dt. Okay, instantaneous change in strain with respect to time. Just a second. Okay. So understand that these two elements that we are representing here, spring and dashpot, are not necessarily representing overall response of any viscoelastic material, right? So you need to combine them in some certain way. You can't use just a spring or just a dashpot to represent the overall behavior. You will need to combine them in some certain way. Then only you'll be able to get some behavior out of it. Therefore, um there are various models which have been developed in order to combine them in a specific way, and these models essentially gives you an idea into how to how different polymer materials could behave in. So this combination of different models are essentially based out of what kind of behavior that we are seeing in a particular polymer material. Okay, just give me a second. Okay, so let's start with the first model, which is the series combination model. Okay, so in which both spring and dashboard are connected in series, and this model was given by Maxwell. So series combination. Maxwell model. Okay. Now there are two ways we can look at this model. Okay, so first thing is, okay, let's first draw the model so that we can understand better. There is a spring followed by a dashpot. Okay, and you are applying the force F here. Okay, dashpot has a constant Kv, spring has a constant Ke. Okay, and we are giving the total deformation. Okay, so what we are doing is we are applying a sudden elongation E. Okay, so first we'll apply sudden force F. Okay, so if you're applying sudden force F is applied. Okay, so let's say we have applied a sudden force F. What will happen? Your total force F will be equal to F1 plus F1 is equal to F2, right? F1 acting on spring, F2 acting on the dashboard. But your total deformation E will be equal to your E plus EV, right? The total deformation. Now EV I have already defined in this way, like using this equation. If you are seeing on the top, this equation is what I use to define EV, right? So I can write, so EV dot is dEV by dt. So EV will be equal to what? EV dot is equal to, let's say, FV by KT. This will imply, let me just move this a little bit to the left. Let's write it in writing so that it's clear. So EV dot was equal to FV by KV. Then if we integrate on both sides, we will get something like this. EV to be equal to FV into T divided by KV, right? If we integrate it. So we can substitute this value of EV here. So we can write E is equal to EE, which is equal to FE by KE, while EV is equal to FV T by KV. Straightforward derivation. There's no difference, right? So this is your strain that we are sorry, not strain, the deformation that we are observing. Yeah, so E is deformation, not strain. It is deformation. Although strain is also fine, but like if you're looking at individual elements, you can also use strain. But here, since we're looking at combined effect, you will use deformation, which is better. So what is happening to your force? Sudden force is being applied, right? So initially your force will increase suddenly, and then it will be flat, right? At t is equal to 0, your sudden force is applied, and then for what is happening to strain with time, at t is equal to 0, suddenly the strain will increase, right? Due to the spring carrying the load. And then, so this value, this sudden increase will be equal to what? Fe by Ke, right? And then it will, so this point is Fe by Ke, then it will keep increasing linearly with respect to Fv by Kv, right? So this is your total value of deformation, E. Okay, so this was sudden force being applied. Now what if I apply sudden elongation instead of force? So instead of applying force, instead of applying load, I'm applying a deformation or elongation, E, at time 0 if I'm applying. So what will happen in this case? So your initially you will get some F naught acting on the spring, which will be equal to Ke times E, right? Now this force will cause your dashpot to operate, right? So this will allow the dashpot, this force will allow the dashpot to operate. So this will gradually increase what? Strain EV, right? If dashpot starts operating, your strain EV starts increasing at a particular time, right? So you can write FV FV will be equal to, sorry, let's just write F. Force at any point will be equal to Ke, Kv, or let's write it as Kv times dEV by dt, right? But at any instant of time, F is also equal to your spring constant times E, right? Now this E can be written as E minus EV, right? So I can write Ke times E minus EV. So if I substitute that here, I will get F is equal to Kv into dEV by dt, which is equal to Ke times E minus EV, right? So now if I integrate, like if I rearrange and integrate, let's say I rearrange this to this form, dEV. So I'll take all the EV terms on the left hand side, all the other terms on the right hand side. I'll get Ke by Kr, right, times what is left, dt. Now if I integrate this on both the sides, okay, left hand side with respect to dEV, right hand side with respect to dt, I will get on left hand side natural logarithm of E minus EV divided by E, right? And on the right hand side, I will get, what will I get? Actually, not just this, you'll get negative sign also, because E minus EV is at, like it is minus EV, right? So there's a negative sign before EV, so it will be negative. So this will be KE by KR times T, right? But there is a term called as tau, which is equal to KR by KE. Sorry, KV by KE. Why am I writing KR? KV by KE. So this will be equal to T divided by tau. Or if I take the negative sign on the left hand, on the right hand side, write it as negative of T divided by tau. So this is your final expression for strain, right? If you solve it further, you can write E minus EV by E to be equal to exponential to the power, and write it as exp, because if I write it as e to the power, then it might cause confusion. So T divided by tau. Okay. And furthermore, from previously we have written E minus EV to be equal to F times Ke, or F by K, sorry. Here, if you see, let me mark it with red, this equation, right? So if I use that here, your E minus EV is equal to F by Ke, right? So E minus EV is equal to F by K, and your F naught, we have already defined initial elongation that we get. Your initial force due to the elongation will be equal to Ke times E, right? What times Ke F naught. So on E can be written as F naught divided by K, right? So on the left hand side, E minus EV I will replace with by F by Ke, and this by F naught by K. So Ke gets cancelled. So F by F naught I will get is equal to minus T by tau, right? Or in other words, your F force is equal to F naught, which is the initial force that you get due to the strain being acted upon, equal to exponential of minus T by tau. Okay. So if we draw the time versus so elongation is straightforward, right? I have applied a sudden elongation. Suddenly it will increase to some value, and then it will become zero throughout. So T is equal to 0. But your force, what happens to your force? Initially it will go to some value which is equal to F naught. Right, F and T. So this is your F naught, right? Now F naught is equal to Ke by E. But once that happens, then it is decaying, right? It is e to the power minus T, right? E to the power minus T, e to the power negative something, which means that E value will decay. It will not increase exponentially. So it will decay, something like this. Okay, so it will decay. So this is your T is equal to. Okay, so in sudden elongation, we'll see a decay of force while elongation remains constant. While in sudden application of force, we will see that the elongation continuously increases as the time passes. Okay. Okay, so this is. I keep adding pages. Okay, so this is one type of combination, series combination. Now let's move to another type of combination, which will be exact opposite of series, parallel. Now this model was given by Voigt. So let's Write down the name also. Void model. Okay. So this is parallel combination. Just a second. Alright. Now, if I just draw what this looks like, it will be something like this. You have one spring on this side, one dashpot on this side. So both of them are acted upon together. Okay. So if I'm applying a sudden force F like last time, what will happen? Last time what happened? When I'm applying a sudden force F, what is happening? The force, what will happen to the force here? In last time when they were in series, what happened to the force? The force that the spring felt was same as the force that the dashpot felt, right? Because they were in series. But here they are in parallel. So the force will get distributed among both the channels, right? So that F will become equal to Fe plus Fv, right? But in elongation, what will happen to that? Both have to move together, right? When you apply the force, both the sides have to move down together. So it will be equal to E plus, sorry, E, which will be equal to Ev, right? So this is what you will see in parallel combination. So when sudden force F is applied at time t is equal to 0, understand that this behavior that I'm writing down here, F is equal to Fe plus Fv and E is equal to E plus Ev, is a characteristic of parallel combination. Okay, it is not a characteristic of whether I'm applying sudden force or sudden load. It is characteristics of parallel deformation. Okay. Okay. So what is happening here is initially will dashpot will carry all the load, right? Right? And then deformation takes over. You will get DE is equal to DE, which is equal to DEV, right? So then the spring will operate. So essentially what is happening? At some t is equal to infinity, okay? Let's take some random time t is equal to infinity. Some very future time very far in the future, you will get E, the strain, E infinity, okay? E infinity at t is equal to infinity to be equal to F by K, right? The spring is completely taking the your strain, completely taking the strain. Okay. So your DEV by dt is given by Fv by Kv, the normal equation. Now Fv is what? Here force is getting divided into two parts. So you can write F minus Fe, right, by Kv. Now what is Fe? Fe is equal to F E times Ke, right? Because E is equal to E, which is equal to Ev. So I can write E E times Ke or E times Ke, which is one and the same, divided by Kv. So if I rearrange, it will be Ke by Kv. If I take them out, is equal to, sorry, into Fe by Ke minus E. Sorry, this is not Fe, this is F. Yeah. Now dE by dt or dEV by dt is can be written as dE by dt is equal to 1 by tau. Right, I've already defined tau to be Ke by Kv by Ke, so 1 by tau. And this I have already written here in this. See the equation I'm marking by red, this part. So this part I can use here. F by Ke is equal to E infinity, right? The strain at time is equal to infinity. So E infinity minus E. This is your d by dt. Now if I take all the strain terms on one side and integrate, so if I want to integrate, I can write this as is equal to dt times tau, dt by tau. And if I integrate on both sides, I will get natural logarithm of E infinity minus E divided by E, right, on the left hand side. And on the right hand side, I will get T by tau. Now there will be a negative sign because when I'm integrating with respect to E, this part has a negative sign here. So this is why the negative is coming. Here there's a negative sign, right? E. And I'm integrating with respect to E only. So that negative sign on the left hand side, I'm just putting it on the right hand side. One and the same. Same thing I have done in the previous case also. So further solving it further, I'll get E infinity minus E is equal to exponential of minus T divided by tau. Right. And if I take out this common, so E by E infinity will be equal to 1 minus exponential of, I'm just skipping a few steps, or your E will be equal to, your strain E is equal to E infinity times 1 minus exponential of minus T by tau. This is your final expression for strain. Okay, final expression for strain. So what we have done, we have applied an instantaneous force F. So if I draw the diagram, an instantaneous force F is applied at time t is equal to 0, and strain will, at t is equal to 0, it is equal to 0, right? Then it is exponentially increasing, right, till it reaches some value. Okay, let me pull it down a little bit. Till it reaches this value, which is E infinity. right? E infinity is equal to F by K. That is, the spring takes over the complete load. Okay. So this is one case for parallel combination or void model, right? Now, what could be the other case? Instead of applying a sudden force, we are applying a sudden extension or sudden elongation. Okay, so now what is happening if I'm applying sudden extension? Immediately as soon as I apply this sudden extension, what should happen? Now in parallel condition, what is the major thing that we have observed? We have observed that whenever we apply an extension, both spring and dashpot should move together and take that extension, right? They cannot have different extensions at different instant of time. Both of them should have same extension, right? So both spring and dashpot should move together. That is one observation that we can make. Both spring and dashpot should move together or extend by same amount, right? Right, both spring and dashpot should extend by the same amount or they should move together. However, when you're applying a sudden extension, what is happening? Dashpot will not be able to take that sudden extension immediately, right? Only spring will be able to extend. Dashpot will not be able to take the sudden extension. Dashpot cannot take sudden extension, right? So therefore, that extension will not manifest itself in the dashpot. And if you have such a condition, then the entire thing will not move only. So it is an impossible condition, right? If spring is able to take the extension while dashpot is not able to, then this condition will not exist at all. So you can write this as an impossible condition. Because spring is able to take the extension while dashpot is not. Okay. You can remember this. That in parallel case, just parallel, if you have a dashpot and spring in parallel, you cannot have sudden extension model. You can only have sudden force model. Okay, so one last thing that we can see, we can have combined parallel and series. Okay, before we move on to the next topic. Combined parallel and series, or series parallel, whatever. Again, this model, since it's a combination of both the models, you can call it as Boyd-Maxwell or Maxwell-White model. Okay. So here what is happening is you have a spring, a dashpot, and you're applying a force here. Okay. So let's take this as K1, this as K2, and this as Kv. Okay. Now, for the top half, your spring K2 and or spring with spring constant, let's say spring 2 and your dashpot are in parallel, right? So what will happen to that part? You will have your EV, to be equal to E2, right? But your total strain will be a sum of this plus this because it's a series. So E1 plus E2, right? You can see here previously what we have done. In parallel combination, your strains are equal, but in series they are added up. Again, parallel combinations, your force should be added up, but in series they are equal. So your force is equal to F1. Now F1 is in series with this dashpot spring combination. So since they both are in parallel, they have to be added up. F2 plus F2. Now this is the condition that we have. Okay. Now, if we are putting a sudden application of force at t is equal to 0, what is happening? Your dEV by dt. So I'm using similar expression as previously, right? I'm combining the parallel and series that we saw previously, and then I'm calculating opposite. So dEV by dt will be equal to Fv by Kv, right? Just like previous case. So we'll have F minus F2 divided by Kv, like the previous case. So F2 is K2E2 divided by Kv. And if I extend it further, like last time only, I'll get K2 by Kv times F by K2 minus E2. Now F by K2, if I represent it as E infinity minus E naught, where E naught is strain due to spring 1. Okay. So if I write this as E infinity minus E naught, where E naught is strain due to right, because strains are getting added up. Okay, so instead of writing it as E, I'll write it as E naught. I can take it further and write dEV by E infinity minus E naught minus E. And let's say I want to integrate it, is equal to dt by tau. So here tau is equal to kv by k2, not kv by ke, kv by k2. Okay, which spring constant we are taking? We are taking spring constant of spring 2, the one which is in parallel. This one, k2. So your EV is equal to, if I solve it completely, I'll get E infinity minus E naught. I'm skipping all the steps in between. You can do the maths on your own. It's the same, it follows the same trajectory what we followed in the previous example. Exact same trajectory. You can do it one by one. So easily. Okay. 1 minus exponential of minus negative of t divided by 2. Okay. So E is equal to, your total strain will be equal to EV by EV plus E1. Okay. Now your E1 here is equal to E naught. Okay. Strain due to spring 1 is given as E naught. So your total strain, again, I can rewrite it as E infinity right. So this is E infinity minus, yeah, so if I solve it, if I substitute and solve this entire thing, I will get E is equal to E infinity. Yeah, just write the final equation, because if I write the whole thing, it is a very huge thing. E infinity minus E infinity minus E naught, okay, times exponential of minus T by tau. Okay, this is your final strain. Okay, so if I draw the graph, it will look something like this. So F is, of course, sudden force I have applied, nothing, no difference. Your E versus T graph is what we are concerned with. So what will happen is, initially, so instead of starting from 0, it will start from some initial E naught value. Okay. So let me mark it here. So this is an E naught value, and then it will tend to E infinity. All right. So this is your E infinity. Okay. All right. Now, similar to previous cases, again, if I want to apply sudden elongation, where we saw parallel. Now, understand that sudden elongation here will still work. Why? Because here sudden elongation is, one second, yeah, here sudden elongation is not just dependent on the parallel combination of spring dashboard, but there's another spring which is present, which will take that sudden strain, right? So we can say that all of the sudden strain initially, so initially all of the sudden strain or sudden elongation will be taken up by string 1. Okay, because when they're in parallel, they will not work together, but when they're in series, they will work together very nicely. So you will have E equal to F by K1. Okay, or you can write initial force to be F naught. So F naught to be equal to K1 times E. Okay. So after a very large instant of time, T is equal to infinity. T tending to infinity. Okay. So E will become equal to F by K1 plus F by K2, right? because now your dashboard has operated and it has completely died down also as well. So you will get F infinity times K1 plus K2 divided by K1 K2. Okay, at time infinite tending to infinite. Now your F infinity is equal to, just rearranging this, K1 K2 divided by K1 plus K2 times E. Right. So your F, the force with respect to time, will depend on both F naught and F infinity. So it will be of this form. If you do all the maths involved, you'll get final expression in this form. Okay, exponential of negative of t divided by tau. Okay. Or tau lambda, let's represent. So here tau lambda is equal to kv divided by k1 plus k2. All right. So this is how you can create different models, different versions of it. Now, not all polymers or not all materials that show viscoelasticity will show specifically one of these three behaviors only. They can show a combination of any type of behavior. Now, essentially, when you're trying to model a viscoelastic material using computational means or some other way, if you're trying to model it, if you're using some mathematical model, if you're trying to do it, uh, you can model it in different ways, right? You will not get one singular type of property. You will not get only series behavior or only parallel behavior or series parallel behavior that we are showing here, right? You might not get a combination like this. You might get some random combinations of springs and dashboards. Okay, so essentially you have to solve the equations in this way. This is what we are trying to show you here. Whenever you get some model, some spring dashboard model for viscoelasticity, you can solve it in this way. This exact same model you might not get in exams or in some other places. Okay, so this is viscoelasticity. I hope I've covered everything. Yeah, I think everything is done. Now we'll move on to tensile testing. Yeah, I think everything is done. Yeah, so let's move on to tensile testing. We'll quickly learn the concepts. I'm sure that most of you will be aware of a lot of these concepts, but we'll just revise them quickly. Okay, so let's look at a stress strain curve first. So some materials have a stress strain curve like this. Okay, actually I think I've done too much of. Alright, so there are different points on this stress strain curve that is important to us. Now, what is the first thing that we have to notice? Okay, let me just write it out so that stress strain. Let's draw the other curve also. So there are two types of curves that we can see in stress strain. Now this first case is normally seen in like aluminium, copper, maybe brass and similar type of materials. While this type of curve is seen in This stress strain curve is seen in medium carbon steel. Now, why we are seeing this kind of behavior in medium carbon steel? Because this is an anomaly. Normally, you should see just a singular behavior, just like how we are seeing in aluminum, copper, brass. Why we are seeing medium carbon steel behaving in this way? Because of the presence of carbon or other alloying additions within the structure of iron. Now, presence of those will cause some sort of strain energy regions, and these regions, when we try to strain them beyond the plastic limit, what happens is the strain energy regions suddenly start getting free when we try to strain them beyond that particular limit. Beyond the plastic limit, the strain energy regions suddenly start becoming free, and because of that, you will see a initial drop in the curve, and then this drop that you're seeing. You'll see that initial drop, and then again, once those strain energy regions have all moved out, you will see the final curve. Again, that is materials. That is more towards material behavior, not into mechanical behavior. So that is not something that we will be discussing in detail in this course, but you can just understand that this is known as Cottrell phenomena. So you can just read up on it if you are more interested into why we are seeing this kind of behavior in medium carbon steels. You can read up on why this presence of carbon etc. are causing the strain energy regions, and then those strain energy when they are freed up, how they act and all. So you can read up go online and read it up on your own time. So coming back to the concept that we are more interested in. So whenever we look at stress strain curve, there are few quantities that we are always interested in. Okay. So first thing, of course, goes without saying, is let's say this point A. Okay. So I'll just try to define it. A is proportionality limit. Now, as the name suggests, proportionality limit does what? It gives us the value up to which, the point up to which stress will be proportional to strain. Okay. Then you have another point very close to A, which is point B. Your OB is the elastic limit. Okay, actually I'll not write it as OB. Let's just write it as A, B, and point A, point B. Okay. Yeah. So what does elastic limit specify? The point up to which elasticity, elastic behavior is retained. Okay, the elasticity or elastic behavior is retained. What that means is, once you remove the load that is acting on the material will regain its original shape and size. Okay. Then there's another point, point C, which is known as yield limit. This is the point beyond which yielding will start happening. Okay. Now, for this kind of material, medium carbon steel, you will see a clear upper yield like YU. Like your yielding will not be a single point in this kind of medium carbon steel. The material showing this kind of behavior, you will have like a region of yielding. Okay, this entire region will be region of yielding. Okay, but you will have an upper yield point and a lower yield point. That is what you will be concerned with. However, for this kind of material, here point C is not something that is very easily defined. So what people do is, the yield limit is not very easily distinguishable. So what people do is they just plot. Let's just take a different ink so that it's clear. So at some 0.2% strain. This is 0.2%. Mind you, it's not 0.2 strain, it's 0.2% strain. Okay. So at 0.2% strain, they will draw a line parallel to the elastic part of the curve. And then wherever it hits the curve, that point is taken as that point C or Y, whatever you can represent it as, which is the yield limit. Okay. Or yield stress, whatever you want to call it. Now, there is this point D. and then there is this point F here. Last 2 points. So D is giving you the maximum value of stress that the material will be able to withstand. So this is known as ultimate strength. While F is giving you the fracture point. Understand that these two curves that I have drawn here represent engineering stress strain and not true stress strain. Okay. If you remember in the last class, we had discussed about what is the difference between engineering stress strain and true stress strain, right? These curves represent engineering stress strain. These are not representative of true stress strain. Okay. Now, why do we why do we need to measure these values? Why do we need to quantify these values? Essentially, each of these points, right, the elastic limit, proportionality limit, yield limit, ultimate tensile strength, or ultimate strength and fracture point, etc., represent some sort of material behavior that we are very much interested in all the time. Okay. Now, these values will give you limits to which you can push the material for a particular application. For instance, if your application demands that you do not have plastic deformation within the material, you should not extend your load well beyond, you should not extend your load actually even a little bit beyond the elastic limit. It has to not extend the elastic limit at all. Similarly, if your application involves materials that are used within the plastic region, you may be okay with loading the material in such a way that they are only that they are operating within the plastic region also. So if you are okay with that, you can do that. Okay. So depending on what kind of values that you're getting and depending on what kind of applications you're using a particular material, these different points will come into play. Okay. Okay. So I think I've already discussed true stress strain last time, and I had asked you to find the relation between true stress and engineering stress, right? So true strain and engineering strain is anyway straightforward. The relationship is anyway straightforward, right? But true stress and engineering stress, I had asked you to find the relationship. So I'll show it to you how to do it today. But I hope like you have already tried it on your own and you've tried to find how the relationship works. Okay, so let's first write the relationship between true strain and engineering strain, just for recalling. Okay. Just okay. So your true strain epsilon t is equal to, okay, let's write small t. Epsilon t is equal to ln of natural logarithm, ln of 1 plus epsilon e, right? You remember this, that we had done this in the last class, how they are related. Now similarly, if I want to write true stress, I had already given you the relation, right? The true stress sigma t is equal to your sigma e times 1 plus epsilon e. This is the relation that I had given you. So how are we deriving this? Okay, so let's write sigma t, the true stress, to be equal to P, the load P divided by instantaneous area AI, right? AI is instantaneous area, while your engineering stress F sigma E is equal to P divided by, sorry, A naught, right? Your initial value of area. Right. So you can write your sigma T to be equal to P times A naught divided into A naught by AI. Okay. But one thing that we have to keep in mind is that whenever this process of stress strain that we are looking at, we will say that the volume is usually conserved. Okay, we have a constant volume. So you will get A naught into L naught to be equal to AI into Li. Okay. Now, so if I rewrite this, if I rearrange, it will be A naught by AI, which will be equal to Li by L naught. Now, what is Li by L naught? Li by L naught was equal to L naught plus delta L divided by L naught, right? Change in length plus original length will give you Li, right? Or it is equal to 1 plus delta L by L naught. Now, what is delta L by L naught? 1 plus epsilon E, right? So I can write A naught by AI is 1 plus epsilon E. So your sigma T will be equal to P by A naught. So P by A naught is what? I can rewrite this as sigma E times 1 plus epsilon E. Right? I can write the final expression directly. I hope this is clear to everyone. There is no doubt as to how I'm getting this expression. Okay, so let's talk about another important concept. So yeah, before we go forward, I'll tell a few things. I think that is not something that we need to note down. So whenever we look at this elastic plastic region, right? Understand in representative purpose, we are seeing that the elastic region is so big and the plastic region is so big. But in actual curves, you will see, like for materials, you will see that the plastic region will be huge as compared to the elastic region. Elastic region will be very, very small compared to the plastic region. Okay. So that is something that you have to keep in mind, that these graphs are all representative. They are not representing exact behavior. Okay. And one more thing that you can keep in mind is, for very, very small values of strain, okay, we can take engineering strain to be equal to true strain. Okay. And similarly, you can take true stress to be equal to engineering stress. Okay. Understand that when you are saying very small values, it would generally mean that we are in the elastic regime and to some extent in the plastic regime. Okay. We are not going too much beyond plastic regime. Okay. General case, you will always have sigma T, okay, the true stress to be greater than sigma E, the engineering stress. While you're in the case of strain, you will have epsilon E to be greater than epsilon T. Okay, engineering strain will be greater than engineering. Engineering strain will be greater than the true strain. So this is something that you can keep in mind. This is the what happens generally in real life. Okay, but for very small values, they'll be almost equal. So you can just take them as. Okay. Next thing that we'll talk about is resilience and toughness. Now, what is resilience? Now, this is the ability of the material to take load within elastic limit. Okay. Ability of the material to take load within elastic limit. Toughness, on the other hand, is the ability of the material, like the total load that the material can take before it fractures. Okay, so you can think about total, not exactly load, but total energy that the material can take before fracture. Now, how do you measure these two quantities? So if you have a stress strain curve, okay, something like this. So if this is your elastic limit, the shaded portion show your resilience. Okay, so this is your resilience. So basically, it's a energy value. Okay, stress strain curve. If you find the area under the curve, you will get energy. So this is energy. So this is your resilience, while your toughness is the total area under the curve. If I draw the same curve, this entire thing this entire area will give you toughness. Okay. So toughness is entire area, entire area under the curve, while resilience is area under the curve till the elastic limit. Okay. So based on different properties, you will have materials which will have high resilience, but they might have low toughness. While some applications might require you to have materials having high toughness but low resilience. So depending on what material system we are looking at, we can talk about resilience and toughness. Okay. Last few things. One is, so this is something that I think is also important for you to know. There is something known as Bridgman correction. Okay. Now, why do we? There's no E here. I think. Now, why are we talking about this correction factor? What is the necessity? Okay. So let me just write down the equation because I don't think there is any explanation required. It has already been given in the videos. So it is equal to 1 divided by 1 plus 2r by a times ln of 1 plus a by 2, where if you are drawing this okay, so if you're drawing a necking region, the radius of this portion and your A, this from the center, this distance A is given by A. Now, why are we talking about this Bridgman correction in the first place? What is the reason behind it? So, whenever we measure stress, right, this is your measured value of stress. In any system, be it UTM, extensometer, etc., whenever we measure stress, we are not measuring the exact value of stress after necking. Okay, so after necking, if you look at true stress strain versus engineering stress strain curves, you'll see that after necking, the engineering stress strain curve will dip after the necking part. It will dip after it hits the ultimate tensile stress, while true stress strain will go straight up. Right. So why this difference is coming? Why are we seeing this difference? Essentially, what is happening is the neck region, right, is also contributing to an extent to the value of stress. Okay, because the region, the area around it is continuously decreasing, but we are not accounting for that decrease in the area while we are calculating true stress, or while we are calculating engineering stress. We are only accounting for it when we are calculating true stress. Now, this difference essentially leads us to believe that the measured stress value is wrong to an extent, right? So if you want an effective value of stress, the corrected value of stress, you can use this Bridgman correction to give you an effective stress value which is more closer to reality, okay, which takes into account this necking behavior and gives you the final value of stress. So therefore, this Bridgman correction has been brought into the picture. Okay. After this, the final thing is something that we need to understand is what device or what machine that we use to measure stress strain in any curve. It is known as, there is one very useful machine that has been developed, which is known as universal testing machine. Now that is very much used all the time for measuring the deformation and load, and from there you can calculate the stresses and strain in the material. Now UTM comes in variety of shapes and sizes. I hope you have gone through the video that was given by the professor. In that they have talked about how different types of UTM are there, what could be the various systems, the electromechanical systems, hydraulic systems, and what costs, etc., would be involved with UTM, and how UTM works essentially. Also, you would have seen just UTM value will also lead to errors, so you will have other things put into UTM, such as extensometers, etc., which will also give you an idea of what is the value of stress together with UTM. Okay. So with that, we will end the theory part of today's class. We'll go to the problems. Okay, so there are few problems that we will discuss for today. Now, first question, they have told us a dog bone-shaped A6061 specimen was subjected to a load of 1 kilonewton under uniaxial tensile loading. The initial gauge length and diameter are 25 mm and 6 mm respectively. So they are asking us to determine the true stress acting on the material if the final diameter is 5.5 millimeter. Okay. So initial load that it is subjected to is 1 kilonewton. Okay. Initial load, let's write F to be equal to 1 kilonewton. Then they have given us an initial gauge length of 25 mm, right? So your Li will be equal to 25 mm. Then initial diameter Di to be equal to 6 mm, right? And finally determine the true stress if the final diameter is 5.5. So final diameter is equal to 5.5 mm. Right. Now, what is your engineering strain in this material? Your engineering strain is equal to change in length by original length, right? But before that, before finding engineering strain, actually, we need to find something more. We need to find the new length, right? The change in length or the new length, something we have to find it. So how can we calculate that? We can calculate that using the concept of volume remaining constant, right? So if volume is constant, your initial length and initial area, the multiplication of that, initial area times initial length, will give you the final area times LF. This side, this is DF. Okay. So if I calculate this, I will get LF to be equal to pi di square. Okay, let me just Li divided by 4. Okay, let's not write it this way. Let's write the whole expression first. Pi by 4 di square Li is equal to pi by 4 df square Lf divided by 4. Now if I substitute for Ai, Li, sorry, not Ai, Di, Li and Df, because those three are given to us already, I will get Lf to be equal to, let me just calculate, just give me a second. Yeah, so final value of LF is coming to be 29.7. So 29.75 is your final value for LF, right? So substituting that back, so you will get engineering strain to be equal to LF minus Li by Li, right? So substituting and solving, you will get 29.75 minus 25 divided by 25. So let me just do that. 0.19, around 0.19. Okay, so this is the engineering strain. Now engineering stress, again directly we can calculate. We know the force, we know the initial diameter. So your engineering stress will be equal to F by A, AI. So AI is equal to pi by 4 di square by pi by 4 di square. So if I substitute, let me just write down the final answer directly. So this is equal to 35.36 MPa. Now, if I want to calculate true stress, I can just do engineering stress times 1 plus epsilon E. Right? We just derived it, how to get that value. So let me just calculate and give you the final answer. .09 MPa is the final answer. So if we check the option, the first option is the correct. Okay. I hope everyone was clear on how did we do it step by step. Okay. Initially we found the value of change in length. So using constant volume, we tried to find the new length. Then using that, we found engineering strain, then engineering stress, and finally the true stress using all the expressions. So just give me a moment. Okay. So next, let's go to the next question. They have told us the true stress versus true strain diagram for a strain hardening material is as shown. The material was loaded initially up to point A, and from there it was unloaded to point B. Okay, they have marked it. Given that the Young's modulus of velocity is E equal to 200 GPa, the strain at point B they are asking. Okay, again a very involving problem, not very straightforward, but they have given us a lot of information directly in the figure, so we can use that to find. Okay. So, what do we do first? Let's write down what and all we know first. Okay. So they have given us E to be equal to 200 GP. Now your OA, right, from O to A, O being this point, so O to A is equal to 400 MPa, right? And your OB is equal to 0.5 times 0.5 minus epsilon B, right? Whatever is, sorry, I think I've taken the wrong point. Yeah, this is O. Yeah. So OB is equal to 0.5 times 0.5 minus epsilon B. Sorry. Yeah. Now, epsilon B here, what does epsilon B here represent? The plastic part of the strain, right? If you see clearly, your epsilon B, your AB is parallel to the elastic part of the stress, right? When it is returning back, when the deformation is removed, when it is returning back, only the elastic part is recovered. The plastic part is not recovered. So AB will be parallel to the elastic region, right? But epsilon B is only the plastic part, which is not recovered. So this is the plastic strain. Okay. So if I write your modulus of elasticity E will be equal to your value of stress at point A divided by whatever is the elastic part of the strain, then we can get the final answer, right? So if I solve this, I can write 200 GPa. So 200 into 10 to the power 3, if I convert it to MPa, is equal to 400 divided by 0.5 minus epsilon B, right? Or epsilon B that we are trying to calculate will be equal to 0.5 minus 200 into 10 to the power 3 divided by 400. Okay. Sorry, other way around. Yeah. 400 divided by 2. Yeah, this makes sense. So if I calculate, So final answer is 0.498. Let's see if there's any other option corresponding to that. Yeah, so third option. Okay. So this was again, all the information was given. We just had to use the figure properly, and then we were able to calculate everything directly from the figure itself. No, not much to do after that once you know how to decipher the figure. Okay. So which of the following represents constitutive equation for viscoelastic material based upon Maxwell model? So Maxwell model we studied, it was series like spring and dashpot in series, right? So they're asking us the constitutive equation. So we know the equations in terms of force and uh, elongation. So now we have to write out in terms of stress and strain. Okay. So force for in Maxwell model, the spring and dashboard were in parallel, right? Were in series. Sorry, were in series. So what happens when they are in series? When they're in parallel, the extension should be moving together. So extension will be equal. But when they're in series, the forces will be equal, right? So your sigma, which is equal to like force by area, will also be equal to sigma E equal to sigma V, right? The stresses will also be equal because the forces are equal. But the strain that we have talked about is equal to, or change in strain we can write, because so that it becomes strain rate, we'll write it as, okay, epsilon E dot plus epsilon V, right? I hope this part is clear. How I'm able to write this. The summation of strain will be in terms of epsilon dot, right? So if I write epsilon dot, furthermore, it will be equal to sigma dot, because sigma is same for both the cases, divided by E plus sigma divided by this n, which is the dashpot constant. Okay. Now if I rearrange, if I take n by E, right? So I take n out from this equation. Sigma I take it outside. So n into epsilon dot will be equal to n by E times sigma dot plus sigma. This is my final expression. So which one corresponds to that? The first one, right? So this is the correct option. Okay, so we are just deriving the same relation in terms of stress and strain now instead of force and elongation, which is what we derived previously. Okay, hope this one was clear. There was no doubt here. Right, let me just check once if everything is right. Yeah, this is correct only. So we'll move on to the next problem. They have shown us White model for viscoelastic material, and they're asking us to find the time required to reach a strain level of 0.99 of the terminal strain, that is E infinity. That is at t is equal to time is equal to infinity. Okay, they've given E is equal to 100 MPa, your n or nu equal to 10 MPa. So this is nu. This is a dashboard constant nu. 10 MPa second, and initial stress to be 10 MPa. Okay. So let's write down what is given to us first. Okay, and your initial stress they have given us. Okay, yeah, initial stress they have given us 10 MPa. Okay, so according to the Voigt model, because this is parallel, right? The dashpot is parallel to the spring. If you can see in the question, according to the Voigt model, we have E infinity to be equal to sigma naught by E, right? Or it is equal to 10 MPa divided by 100. So 0.1. Now the time required to reach a strain level of 0.99 we can write using this equation. E is equal to E infinity times 1 minus exponential of minus of T by, we'll use a different bracket outside. Right, this is the expression that we had derived in Voigt model. Okay, you can just go back and check the expression. So essentially they're asking us to find for 0.999 E infinity. E infinity times 1 minus exponential of minus T divided by tau. Okay. Your tau will be or 1 by tau will be equal to, well, let's solve this first instead of doing that. So E infinity gets cancelled, right? So this will become 1 minus 0.99 is equal to exponential of minus T by tau. So 1 minus 0.999 will be equal to 0.001. Right? Straightforward maths, not much to do here. So your time constant 1 by tau is equal to E by mu. Yeah. So it will be 100 MPa by 10 MPa per second. So this will be 10 8. This is 10 MPa per second, right? Yeah. So this will be 10 seconds. And your final, if you substitute for tau here, or substitute for 1 by tau directly, exponential of minus 10 t will be equal to 0.001, right? So minus 10 t will be equal to natural logarithm of 0.001, or t will be equal to negative of divided by 10. Okay, so let's calculate this. So your final answer is 0.69 seconds. No, this is your answer. Okay. So once you know the models or you know the equations, you can directly solve them. In case you don't know that, then you can just go back, look at the model, and then or create the model. In case the model is something specific, you can create how to find the values, particularly for this particular case. Okay. So the next two questions are theory-based questions. Let's just read them and see what is the answer. Elastic limit is the point in stress versus strain diagram up to which stress is proportional to strain. No, that is proportionality limit. Up to which, at which elongation takes place without application of load. No, that is not right. Up to which, if the load is removed, original volume and shapes are regained. That is correct. Material starts deforming plastically. That is wrong. So this is C is the correct option. Next question, which is the most important property used in metal working process? Hardness, toughness, resilience, and strength. Now, hardness is something different. You don't need that for material working process. So, material working is essentially your what is happening in material working is you are essentially deforming the material and trying to shape it into a particular way. So, essentially, you are taking some metal sheet and you are trying to deform it in such a way to create some different type of sheet, etc., etc. So, that is material working. Now, what is that related to? Not hardness, of course. Hardness is a surface property. Toughness, maybe. Right. Resilience, no. Resilience is only within elastic limit. We are deforming the material, so we are trying to work within the plastic limit. We're working in the plastic range. Strength, okay, it may be important, but the most important property here is definitely toughness, because you have to look at the material behavior, and based on that you have to predict whether the material is able to take, we should be working in a region where toughness is involved without breaking the material, without fracturing the material. Okay. Next problem is again something that we need to solve. So they have asked us they have given us a stress strain behavior for a particular material. They're asking us toughness. So now we know toughness is basically area under the curve, right? Area under the entire curve. So if we divide it into three parts, one part from, okay, let's just name it O to A and then D. And let's say there's one line which is drawn here. We just say M. Okay. So O to O A B. Let this point be B. Okay, and let this point be C. So O A B is a triangle. So for that triangle we have 70. No, not 70. What is the value? Let's take it as 70. I think it's 70 only. They have not marked it correctly. Yeah, it's 70. This should be 60. I think the figure is not right. This point is 60. Yeah. This point. So that should be 70. Yes. And that should be 120. Yeah. So point A is at 70 MPa and 0.004 strain. And point D is at 120 MPa, 0.012 strain. Okay. So area of OAB, so toughness will be total area. Right. So area of OAB plus AMBC, right? The rectangle, and then again the triangle above that, AMD, right? So that is equal to half of 70 into 0.004, okay, plus this is 0.004, 0.012 minus 0.004, so 0.008 into 70, 70 minus 120, so that is 50, right? Plus, sorry, this is 70. This is also at 70, right? Yeah, so this is 70 plus half into 0.008 into 50. Right, that will give us the toughness value directly. Let's just calculate it. So your final answer is 90 into 10 to the power 4. Newton per meter square. Okay. So not square, meter cube it should be. No, meter square only it's correct. Why did they give the question in meter cube? Why have they asked it in meter? I think this question is wrong. Newton per meter square. Yeah. So your C option is the correct one. Okay. I hope everyone is clear on this. So let's move on. Next question. Which type of UTM will have easy amplification of forces? So they have given us 4 types of UTM. Screw-driven, linear motor actuated, servo-hydraulic and electromagnetic piston. So easy amplification of forces would mean that you apply very little force for it to move by a large amount. So that is majorly seen in hydraulic or servo-hydraulic type of UTM. So you can take that. Now next question is, tensile test performed on universal testing machine measures. What does it measure? Does it measure true stress strain? Does it measure Young's modulus and Poisson's ratio, engineering stress and engineering strain, or load and elongation? Now this is something to think about, right? Of course, we know that it does not measure true stress strain or Young's modulus and Poisson's ratio, right? It does not measure that. We know that. We are very clear on that. But do we know what it measures exactly? Does it measure engineering stress, engineering strain, or load and engine elongation? Now, this is something that I had also talked about in the first class. Stress is something that is very abstract. That does not exist in reality, right? It is something that is happening internally to the material. It's a ability to resist deformation, right? So it is happening internally to the material. So that is not something that you can measure as such. You can get stress as a function of something else. So even UTM is able to only measure how much load is acting on the material and how much elongation is happening to the material, right? And then from there we can derive stress and strain. So UTM, although you can see UTM in your, like in labs or something, you can go and check it out. You'll see that when you are looking, when it is connected to a computer, you will see that stress strain plot is getting plotted, right? Stress strain curve is getting plotted. But that is not what it is measuring like initially. Initially, it will measure load and elongation, and from there it will convert it into stress and strain. So in many of the UTMs that you will see in today, like you will see that load elongation curve will be plotted along with stress strain, because load elongation is what it is measuring, and then it is converting that into stress and strain and giving you the final value. Okay, so this is your answer. And your final question: in a tensile testing of a known alloy, the elongation observed to be erroneously higher than that generally observed for alloys. The possible causes of error are. So there are multiple causes that could have happened, right? So you are seeing that the elongation is higher than that what it should be seen, right? So there could be multiple causes. So first cause they have told us is extensometer was not used. Of course, this is a very important thing. If you don't use extensometer, then you might not get exact value. So this could be one of the reasons. Machine stiffness is very low. Now, if the machine stiffness is very low, then the machine would also face some sort of strain, right? The machine will also undergo some sort of training when like you are straining the alloy. So because of that, some strain that is getting added to the alloy straining is also the machine straining. So therefore, machine stiffness being very low is also bad. So that also would be one of the reasons. Micro slip occurred across the gripping end. Now see, wherever you're gripping the material and you're pulling it, at that point you might have some slip happening, right? If the grip is not put very tightly, there might be some slip happening. So that micro slipping might also influence the strain. That is also one of the options. And testing what's carried out at slow strain rate. Now that is not something that we are worried about. If it is carried out at slow strain rate, it is very much better than carrying it out at fast strain rate. So that is not one of the reasons. So the first 3 reasons could be one of the reasons. So that is the final thing. So with that, we'll come to an end for today's problems. I hope everyone was able to follow along, and we have understood viscoelasticity and the concept of tensile testing along with the problems that we have solved today. In any case, if there are any doubts related to this chapter or anything, we can cover that in the upcoming classes, or you can also ask it on the portal. Okay. So with that, we will end today's session. I thank everyone for attending and everyone for watching this. So we'll meet again next week from 6 to 8 p.m. Okay. Thank you.